Okay, so we had started talking about the efficiency of the vector operations, in particular with allocating additional memory, and I told you, or we talked about how many operations would be necessary if for every pushback the memory that's allocated to a vector would have to grow by just that one element. And we are looking at a 500,000 element vector, no, 500 million numbers, yeah, 500 million element vector, then we'd be facing 500 million allocations or increases of memory. Whereas if we always double the memory that is allocated to a vector, then we get by with about 27 memory allocations. And since memory allocations are expensive, that difference in the number of allocations makes a huge difference in running time. Okay. So there's now two different concepts that we have to distinguish, because a vector has memory that was allocated to that vector, and a vector has elements that are actually stored within that memory that was allocated to the vector. You see, it's not the case that, I'm on slide 72, it's not the case that every cell that is allocated to the vector is also occupied by data that's stored in the vector. It might be the case that there is a little excess capacity because we always grow the vector to be twice as large or to have twice as much memory available as before, even though we don't use up all of those memory cells. So clearly we have to distinguish those two concepts. We have to distinguish how full is it and how much memory has been allocated to it. And of course, the amount of memory that has been allocated to it is always going to be at least as big as the number of elements that we have stored in it. That should be clear.
Can you make a program of raising the vector size?
Vector size or capacity. There's now two different terms that we have to use for those two different concepts.
Okay.
One is the size of the vector, and that is the actual number of elements that we're storing in the vector. And the other one is the capacity of the vector, and that is to how many elements can the vector grow in size before additional memory has to be allocated. Yeah, so how much memory has currently been allocated to the vector? Yeah, so is your question how can I grow the size, or is your question how can I grow the capacity?
My question is when can I change it and how do I change both?
Okay, so whenever you do a pushback, you're changing the size of a vector. Okay?
Okay.
Because you're adding a new last element, so the size is one more than it was before.
It just increases by one.
Yes.
Okay.
Then when you do a declaration with this alternative form, you say something like vector int v. This is when you're changing the size also. So this changes the size also, because normally if you wouldn't use this alternative constructor, if you would use a default constructor without this, then you generate a vector of just 0 elements in size. With this, you're generating a vector of 1,000 elements in size. So that's about the size. Now, what about the capacity? Well, the capacity might grow with a pushback. It doesn't. I mean, the whole discussion of last time was that we want to, or people want to implement vectors in such a way that not every pushback triggers a growth in the capacity. Yeah. But obviously, since we're not allocating all of memory to one vector, if we keep growing the vector in size, then eventually the size will be so large that the capacity has to grow. So a pushback might trigger a growth in the capacity, but we hope that few such pushbacks need to do that.
What would be the capacity for that initialization?
Well, see, how the capacity really grows, that is a matter of implementation. So different implementations of the vector library can do that differently. Yeah? So there's no clear answer to that. It's implementation dependent. In this example that I showed you, where we start out with a vector that has a capacity of 4 initially, and then it would grow to twice the size every time around, well then the capacity of this vector here would need to be 1024 elements. The capacity, even though the size is 1000, because that just happens to be the next power of 2. Okay. Now, there is a way to explicitly grow the capacity, and that's on the next slide. There is a member function call of the vectors that you can use to explicitly grow the capacity. This is something that you would do if you know that you have a loop coming up in your program, and that loop is going to push back whatever, very many elements. And you know how many elements that will be, and you want that loop to run as fast as possible. So the loop shouldn't trigger any, no, it should do pushbacks maybe, but it shouldn't trigger any growths in the capacity.
Right.
So you grow the capacity beforehand to a size large enough, and then you're sure that your pushbacks that are triggered by the loop, they're not going to, no, that are done in the loop, they're not going to trigger a growth in the capacity. So you'd use this reserve member function call. Reserve 32 means you want to make sure that the vector is large enough to hold 32 elements. It might be that it allocates more. You don't care. You want it to be able, you want the capacity to be large enough for it to hold at least 32 elements. In the second example, we want 10 more elements. So that's relative to the current size. We're sure that we're going to add 10 more elements, and we want these additions to not trigger any growths in the capacity. So we grow the capacity right from the start, and then we can add those 10 elements without triggering a growth in capacity. Any doubts or questions, anybody?
If you use that inside a function,
Of course, yes.
It goes back, it's the same size as it was before.
Excuse me?
If you use it inside a function, it goes back to the same size outside of the function.
Well, that depends. Are you thinking about a vector parameter to a function? Well, it depends. Is that a call by reference or a call by value?
Yeah.
Oh, and of course, I mean, where there is a way to grow, there's also a way to shrink. That's quite plausible, right? So there's also the member function resize, and that truncates the vector to as many elements as you pass as an argument. So if you say resize 24, then everything after element 24 gets tossed.
Let's say you reserve 32 elements like it says in the slide. What if your loop or whatever you do goes beyond that?
It would trigger. It would trigger.
It would still grow?
Yeah, it would grow, yeah. It would trigger additional growths in the capacity. Let me correct this. Precisely stating, what you're doing with the reserve is you're saying I need at least 32. Now it might be that the implementation is such that if you require at least 32 elements, that it actually allocates space for 128 elements, just for example. Yeah? But once you get to that capacity, once you actually use up all those 128, then you're triggering additional growths in the capacity.
Is there a resize for strings, if possible?
Good question. I would imagine so, but I am not 100% sure.
Because it wasn't put in the slides or anything that we
No.
saw.
Google it. Okay. Who of you thinks that you know how to declare and initialize a vector of 10 doubles? Declare and initialize a vector of 10 doubles.
How about the 10 part?
Okay, I'll give you this much. Double goes here.
Yeah.
Yeah, right. Exactly. Okay. Then here's the question, right? Can you write code to increase the size of a vector? Pushback.
And resize.
Resize increases the capacity, but not the size, because the reserve doesn't it doesn't create any new elements, right? So it grows the capacity, but it doesn't grow the size. Okay, and yeah, we've just talked about the difference between vector size and capacity.
Can you go over it one more time?
Absolutely. The size refers to the number of elements that your program has stored in the vector. Yeah? Whether they come from this kind of initialization or whether they come through pushbacks, that is irrelevant. The size of a vector right after this would be 10, and then if you would do a few more pushbacks, let's say 7 more pushbacks, then you'd have size 17. So that's the one concept, the number of elements that your program is actually using in the vector. And then there is the number of elements that in the memory space that was set aside for the vector can be accommodated. How many elements can be accommodated in the size of memory that has been set aside for the vector? And that is the capacity. And it's always going to be at least as large as the size. Otherwise, you've overwritten beyond the capacity, and what happens is completely undefined. So, is it?
Oh yeah, I got
Yeah.
it.
Okay, so that completes chapter 8. Let me quickly.
So does each pushback give assign a value?